what did we see? We saw that if we take a holomorphic means function which is differentiable function, then it satisfies CR equation. And we had also seen that just satisfying CR equation is not good enough to deduce complex differentiability. Okay, so the example we had seen, and we saw that only CR equation does not give us differentiability. So what was the theorem? If you remember, I had stated that let U be some be an open set. Let's say Z naught is a point in U, and F from U to C be such that F satisfies, or rather, right? Let me write Fy Fx Fy exists and at Z naught, or maybe Fx Fy exists everywhere, exist in U, and Fy is equal to I times Fx and Z naught. If Fx Fy are continuous at Z naught, then F is differentiable at Z naught. Okay, so I have that the partial derivatives, they do exist, they satisfy the Cauchy-Riemann equation. Then we will be able to say that the function is differentiable, provided we also have that the partial derivatives are continuous. Okay, so fine. So let's try to prove this one. So the proof is going to be slightly lengthy. So yeah, you need to follow that. Okay, so we are going to do the following. So let us write f equal to u plus iv, exactly as before. And now what do I have to show? We have to show, so to show that limit h tends to 0, f of z naught plus h minus f of z naught divided by h exists. Right? So this is the thing which I have to show, that this limit exists. Okay, and now you see I want a candidate. Okay, so I want to show that this limit exists, and this is a very common phenomenon that when you want to show some limit exists, you try to imagine what could be a possible candidate. Okay, now for instance, we have seen already this, that for example, if I take my h along the real axis, then you will know that this limit is going to be nothing but what? Tell me what it is going to
Real
be.
part limit.
Yeah, so fx, right? So if I, for example, I want this limit to exist, so no matter, like if I take some specific path along that, also this limit should exist. So in particular, if I take the path along x-axis or the real line, still that limit should exist. And therefore if you now you know that in this limit, if you take h to be real, then the actual limit that you are supposed to get is going to be fx and z naught, fx and z naught, right? Okay, so therefore that's our natural candidate. Okay, because if for some particular path it is fx and z naught, and I want to show that the whole limit actually exists in general, so therefore that limit also has to be fx and z naught. Okay, exists, and the limit is fx and z naught. So this is a candidate which is means reasonable one. That is this I can write it as ux of z naught plus ivx of z naught. Okay, anyway, so that will be it. Okay, and we have to see how we can get that. Okay, so here I have this increment h, so let us also write let us write h equal to a plus iv. Okay, exactly, because it could be a complex number, so like h could be a complex parameter, so I am writing it as a plus iv. Okay, so let us now see. Now, as I said, I have to prove that the limit is ux of z naught plus I times vx of z naught. Okay, so I'm going to calculate this whole thing, this limit, by separating it, separating the real part and the imaginary part. Okay, so let's try to do that and see what do we get. Okay, so for example, let's write down. So u of z naught plus h minus u of z naught divided by h is equal to u of, for example, now again I have a complex variable, but I will immediately switch to writing in coordinates. Okay, so here I should have written this, and z naught equal to a naught plus ib naught. Okay, so I will also switch to the component wise writing. Okay, I don't want to write I. Anyway, effectively there is no difference. A naught b naught divided by a plus ib. This is what I have. And now what I am going to do, I am going to add and subtract two terms. So which is b naught plus b minus u of a naught plus a comma b naught divided by a plus ib, and then I have plus u of a naught plus a comma b naught minus u of a naught b naught divided by a plus ib. Okay, so I have just added and subtracted, and now here of course you see the increment is only on the y coordinate in the first part, and here the increment is only on the x coordinate. Fine. So therefore if I try to adjust the numerator and the denominator, I will write this one as b divided by a plus ib times u of a naught plus a comma b naught plus b divide minus u of a naught plus a comma b naught divided by b. Okay, so you see I have increment only in y-axis, and I have just divided by b that one. And similarly here in the second sum I have increment in the x-axis, so accordingly I will adjust my things. So a divided by a plus ib u of, sorry, not b, u of a naught plus a comma b naught minus u of a naught b naught divided by divided by a. So now therefore what can I write? So the first guy is b divided by a plus ib, and then here you see the increase is only in the y coordinate, so this is going to give me u of y of a naught plus a comma b naught, right? Okay, no, sorry, I should write something else. Yeah, so this one would be okay. Here you see now what I want to do, I want to write this one in terms of the u of y, this function. So here what happens, you see I am taking the values between b naught plus b and means from b naught to b naught plus b. Okay, so I was exactly telling you just a few minutes back that we were going to use what do you call mean value theorem for one variable. So here what I am going to do, you see here only my x-axis is fixed, my x coordinate is fixed, my y coordinate is changing. So for example, if this is the point a naught plus a comma b or b naught, and then this one is a naught plus a comma b naught plus b. So I am only my points are, as far as this summation is, this particular summand is concerned, I am only varying my b over here. Okay, so therefore the change is only in the y coordinate. So what I am going to do, I am going to write this first term as uy of a naught plus a times b naught plus lambda b, and similarly the second one will be a divided by a plus ib. I will say what is lambda, and then again ux of a naught plus, let's say, mu a comma b naught. Okay, where, let me write, where lambda 0 less than lambda comma mu less than 1. Okay, so this is exactly the point which I was trying to make. It's good that Abhishek asked. Exactly, this is the point where I want to use this what do you say, the mean value theorem. And here I see that I have increment only in one direction and the other components are fixed. So definitely what I'm going to do, I'm going to treat this function as a function of one variable taking values in R, and therefore you now just so therefore you can just ignore this one because this is just x coordinate and that's fixed. So only y coordinate is varying, and these are all real valued function. So therefore I can just say that okay, good. So it looks like exactly the mean value theorem as you would have written f of x plus h minus f of x divided by h. So that would look like some f prime of some x plus c, or like ch, where c belongs to 0 and 1. Okay, so exactly that is what I have done in the both cases. Fine, do you all agree to this?
Yes, sir. Yes.
So that's a good point which Abhishek mentioned, and immediately today we see the application. Okay, great. So if anybody has not followed and would like to work it out, so this uses, let me write it down, this uses MVT for real valued functions of a real variable. Okay, fine, great. So now similarly what I am going to do, I have taken care of this guy u. Okay, and now I have to take care of the guy v. Okay, so v of z naught plus h minus v of z naught divided by h. I need to take care of that, and you will be able to do it. I'm just going to write it directly. You will do the calculation if you wish. So b divided by a plus ib, vy a naught plus a comma b naught plus, let's say, lambda prime b, and plus a divided by a plus ib, vx, yeah, it should be vx a naught plus mu prime a comma b naught. Okay, where 0 less than lambda prime comma mu prime less than 1. Okay, so exactly the same kind of analysis I can do, and I'll get this. Fine, very nice. Okay, so now what I am going to do, I'm going to do the following. So let us now calculate this. This means, like, what do, if I put all of them together, then what do I get? Let's see. Okay, so if I put f of z naught plus h minus f of z naught divided by h, what do I get? Okay, so first of all, let us try to collect the terms with the coefficient b divided by a plus ib. So here what do I have? I have ui of this guy, ui of a naught plus a comma b naught plus lambda b, and here I have vy of a naught plus a plus b comma b naught plus lambda prime b. Okay, and remember, each of this lambda and lambda prime, they are between 0 and 1. Okay, so for example, if I take my h tending to 0, then your b will tend to 0, and therefore what will happen, that this point is going to go to a naught comma b naught. Okay, so that should be clear. So let us write it as uy of z1. Okay, whatever the point may be. So uy of z1 is another variable, and the next one would be plus vy of z2, a separate point, or there should be I times, because f is u plus iv. Similarly, plus a divided by a plus ib, I have vx of z3 plus, sorry, ux of z3 plus I times yeah, I times, let me see, what did I do? I think I wrote it wrong. Yeah, ux of x3, that's fine, and then I vx of z4. Okay, so I'll explain what are these xi means. You can understand what are these z1, z2, z3, z4 are, but I will write what is their property, where mod of zi minus z naught goes to 0 as h tends to 0. Okay, so as h tends to 0, all these zi's are going to close to z. So for all 1 less than or equal to I less than or equal to 4. Okay, so therefore this difference that I have to the term that I have to calculate, f of z naught plus h minus f of z naught divided by h, I could write it as some b of a plus ib uy of z1 plus I times vy of z2, and a divided by a plus ib ux z3 plus I times vx z4. And what are the properties of these zi's? These zi's are points which are going close to z naught the moment, like when as you take h naught, h tending to 0. Okay, So if your h is going towards 0, so we see that all these zi's, they tend to z0. Okay, fine. Let's keep it like this. Now what do I have? I need to write down what is, of course, I said that I want to show that this, as h tends to 0, goes to fx of z0, right? So I need to write down what is fx of z0, and then I need to show that the difference goes to 0 as h tends to 0. So let us try to write down what is fx of z0, and I would like to write it exactly in this kind of a form. Okay, so let us see what do I have. So I have fx at z0 is, I can write it as, let's say, b divided by a plus ib, or let me write it the following way. So this is, I will write a plus ib divided by a plus ib fx of z0, and then I will say that you will agree that this is nothing but a divided by a plus ib fx of z0 and plus b divided by a plus ib. Now I times fx is what? By definition, or by hypothesis, I times fx is fy. Very good. So I can write this as fy of z0. Well, fine. So therefore, now if you try to separate it out, let's write one more step. A divided by a plus ib. Fx is what? Ux of z0 minus, or sorry, plus I times, tell me, u, sorry, vx
plus z, vx of z0,
plus then b times a plus ib. What do I have?
vx, sorry, uy of z0
Plus I
plus
times
vy of z0.
I of z0. Very good. Okay, so now let's try to observe. Why did I write like this? Let's try to observe the way I have written this term and also fx of z0. Okay, so you see here, what do I have? I have uy of z1. Correspondingly, I have here, sorry, with respect to b, I have uy of z0. Similarly, I have vy of z2. I have vy of z0. I have ux of z3. I have ux of z0. I have Vx of Z4, I have Vx of Z0. Okay, so do you see the parity clearly? All of you?
Yes, sir.
Yeah. Okay, so now I think like the proof is essentially done. I really don't have to say much. Now, if I try to really calculate this difference between f of z0 minus f of z0 plus h minus f of z0 divided by h, and if I subtract fx of z0, and then if I try to calculate the difference, what am I going to get? I am going to get something which is going to exactly work out very fine, and you will see where exactly I need my other hypothesis. So let us try to write it down explicitly. So let us say mod of f of z0 plus h minus f of z0 divided by h minus fx of z0. This is what I want to calculate. And this one, lo and behold, what I can see is less than or equal to, let us say. So here I am going to ignore a lot of i's, because those i's, they do not contribute anything to absolute value, and anyway I'm going to use triangle inequality. So what do I get in absolute value? This is, let's say, a plus a times ib times the first thing which I would like to pair up is ux of z3 with ux of z0. In absolute value, ux of z3 minus ux of z0. And let us put this one like this. Why there are so many? Okay, plus in absolute value, I can also write vx of z4 minus vx of z0. Vx of z4 minus vx of z0. What happens? Okay, and plus b divided by a plus ib in absolute value, again uy of z1 minus uy of z0, z1 minus uy of z. What is going on? Uy of z0 plus uy of z2, sorry, this will be ux of, no, sorry, this one will be, let me see, yeah, this one will be vy.
Vy.
Thank you. So vy of z2 minus vy of z0. Fine. Okay, great. I have this. Sorry for all this technical issues. Yeah. Okay. So I have this particular inequality. Now, what do I know about all the zi's? As h tends to 0, what can I say about all the zi's?
Right, test to Z.
Yes,
Tends to
Z mod of
Z0.
Z0.
they can go, they go to z0. Now what do I have additionally about the means partial derivatives? What hypothesis do I have here?
They are continuous.
Continuous.
They are continuous. So if they are continuous and zi's are going to z0, then what can I say? What will I be
They are
able to
They'll
add?
go to functional values.
They are
So in particular, as h tends to 0, this term goes 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 to 0. Correct?
yes.
All these four
Yes,
terms really they go to 0 because of continuity of the partial derivatives. And you might say, sir, there is something which is in front of you that is also, that can also go to 0, like I have a 0 by 0 form, but I am not going to bother about them, because what I will do, I will just replace these things, I will forget them, because anyway in absolute value a divided by a plus ib is something which is less than or equal to 1. Similarly, b divided by b divided by a plus ib in absolute value is something which is less than or equal to 1. So I can forget them. Okay. So even if I forget them, I see that difference of this guy can be written as, like, can be bounded above by sum of four things where each of them are going to 0 as h tends to 0. So this implies limit h tends to 0 f of z naught plus h minus f of z naught divided by h is fx of z naught. Do you all agree to the proof? Yeah.
Yes, sir.
yes, sir.
So therefore,
Yes, sir.
you see, it was very simple proof, but it used means all the hypotheses that we had at means various stages. So first of all, we started by saying, okay, what would be our limiting candidate? We identified that it could, we can, let's say we can say that fx of z naught is our limiting candidate, and then we had actually calculated what would be exactly f of z naught minus f of z naught plus h minus f of z naught divided by h, separating out the real part and imaginary part. We did it, and then when we put them together, what we saw is that we could write them as some constant times uy of z1 plus I times vy of z2, again some constant times ux of z3 plus I times vx of z4. And the properties of each of these zi's were that they go to 0 as h tends to 0. And now the only thing that we had to do is that we had to write this fx of z0 exactly in the same form. Okay, so we broke it, we introduced this a plus ib divided by a plus ib, separated it out, and we got at place I times fx. We know I times fx because of CR equation, it is equal to fy. We substituted that, and when we separated the real, means when we wrote f as real and means in terms of real and imaginary part, we saw we are having a form which looks absolutely manageable. Okay, so when we took their difference, they came out in such a nice form. And of course in the beginning they had a factor, but that factor in absolute value is less than or equal to 1, so I don't have to bother about them. And each of the four terms that were effectively controlling the difference, each of them are going to 0 as h tends to 0. So therefore what I get is that limit h tends to 0, f of z0 plus h minus f of z0 divided by h is equal to fx of z0. Okay, so therefore hence f is differentiable at z0. Okay, so it's a simple proof, little lengthy, but nevertheless we have this. Okay, fine. All of we are good with the proof of Cauchy-Riemann, the converse of Cauchy-Riemann or partial converse of Cauchy-Riemann. Yeah.
Yes, sir.
Okay, great. So now let us see some example, one more example, and I will introduce a new notation which I am going to use in place of differentiability. Okay, so let us look at this example. So what is the example I am interested in? I am interested in this example: f of z is equal to mod of z square. Okay, so I am taking this function on C. So if I want to write as a function of x comma y, it will be x square plus y square. Okay, so that's my function. Okay, now I want to understand where are what are the points where this function is differentiable. Okay, I want to understand that. So tell me quickly, do the computation and tell me quickly what are the points where this function is differentiable.
0, 0.
Okay.
0, 0, 0.
X is 2x, if y is 2y. So if I want to say that 2y is equal to I times 2x, so therefore what do I have? What can I say now? So Cauchy,
CR hold.
sorry.
Folds of
So 0, 0 per CR equation hold.
Yeah, okay. So that will be true because both these are real numbers, x and y are real numbers. So the CR equation will hold true only for the point 0. Okay, so CR equation holds at 0, z equal to 0 or 0, whatever it is. Okay, now so therefore we can say f is differentiable at 0. So are there any other points where CR equation holds? No, right? Only at z equal to 0. So f could be differentiable only at 0. But can I say definitely that it is differentiable at 0?
Yes, sir, because fx and alpha are continuous.
Very good. So what we see that CR equation holds at 0. So that tells me the only possible point where f could be differentiable is equal to 0. And now, since the partial derivatives are continuous, we can also say that actually f is actually means differentiable at 0 only. Okay, so it's differentiable only at 0. Okay, now the point is we are not going to be interested about such functions which is nowhere differentiable except at one point or such discrete points and things like that. So we are not going to be interested, or we will not study these kind of functions. Rather, we want to study some functions which will have differentiability in a neighborhood. Okay, so therefore I introduce the following notion. Okay, so this one which I'm going to use from now onwards to in place of differentiability. Okay, so what is the notion? So let U subset C be open, and f from U to C be a function for Z in U. We say f is holomorphic at Z if f is differentiable in a neighborhood of Z. Okay, so I will say that f is holomorphic at a point if the function is differentiable in a neighborhood of that point. Okay, so for example, as per this definition, I will not call in this example whatever f we have seen, I will not call it that f is holomorphic at 0. Okay, so it's only one point where f is differentiable. So in by saying that my function is holomorphic, I am asking something little bit more. What I am asking is that I am asking for function to be differentiable in a neighborhood around that point. Okay, so however small neighborhood it could be, but I need the function to be holomorphic in a neighborhood of that point. Okay, now if f is differentiable on U, then clearly f is holomorphic at every point of view. Okay, so that's kind of clear, right? So if to start with, f is differentiable on an open set, it's holomorphic. Okay, so as far as the analysis is concerned, I'm not losing much. Okay, because anyway, in real analysis also you have taken functions which are differentiable in an open interval and things like this. So here, if I, let's say if I start with a differentiable function on an open set, then like, or yeah, on an open set, then what I am going to have that it's going to be holomorphic at every point of u. Okay, and similarly, if a function is if a function is holomorphic at every point of view, then you will say that f is holomorphic at u. Okay, fine. So is this notion clear?
Yes, sir.
Yes. Yes. This is slightly asking slightly more than being differentiable at a point. I'm asking that the function should be differentiable at a neighborhood of that point. Okay, that is what I am asking. And as I said, if you start with a differentiable function in an open set or already, then for every point in that open set, you will anyway get the function to be holomorphic. Okay, fine. So this is the definition that we are going to take, and we are going to work with it. And another, so here I have a notation. So you will see later, often in place of open set, I'm going to work with open and connected set. We will see why. Because for open and connected sets, we have certain properties which are slightly different for only open sets. Okay, so for most of the cases, we will see that we will work with a domain. Okay, so I will generally denote D by a domain. Okay, so domain means open and connected, and therefore this will be path connected, not only path connected, it's going to be polygonally connected and all of that. Okay, so open and connected anyway. So I will mostly work with domain, and the notation of set of all holomorphic functions on D will be HD. Okay, so this is set of all holomorphic functions on D. Okay, or differentiable functions on D, whatever you want to say. But yeah, as far as the open sets are concerned, they are the same. Okay, so this is what will be the kind of standing notations that we will be using from now onward, and we will use that. Okay, so for example, so the usual examples that we have seen, z, z square, polynomial, all these are holomorphic functions on whole of C. Okay. So as I said, there is absolutely no difference. Okay, now what we are going to do, we are going to see some application of CR equation, and we are going to compare certain things that we have seen in the means in real analysis, and now we are going to do it in complex analysis as well. Okay, so let me see what do I want to say here. Just a moment. Yeah, so this one is this one. Okay. Yeah, so now let us do some application of CR equation. Actually, yes, I want to talk about some application of CR equations. So let me begin with the following lemma, which you have seen it in the real analysis, and we are going to have it here as well. So what is the lemma? So let me see. Once I do this, what do I want to do? Yeah, I want to do this. Okay, fine. So lemma is let D be a domain and f is real valued function on D. Okay, so I have a domain and I have a real valued function on D. Suppose the partial derivatives suppose the partial derivatives fx fy vanish identically 0, vanish identically on D, then what can I say about f? Okay, so what is The lemma is trying to figure out real valued functions on a domain whose partial derivatives vanish identically. Okay, so it's a function of two variables but taking values in R, so like the real part and the imaginary part. And what I am saying is that the partial derivatives of such a function, like both the partial derivatives are vanishing identically. And then what can I say about the function itself? So what do you think? What will be the function?
Constant.
Yeah. So exactly like in real analysis, you had seen that if the derivative vanishes identically on an open set, then the function will become constant. So then f is constant on D. Okay, so let us see this. Okay, so fine, let's do that. So proof. So proof will again be somewhat similar. Okay, so therefore let's see what do I get. Let us write down. So let x1 y1 or x and x2 y2 is in D. Okay, now what am I going to do? I am going to do the following. So we know that x1 y1 and x2 y2, so I have to show that the functional value at these 2 points are same, right? So it's constant, so the functional value at these 2 points are same, and I have the only property that I have is that the uh, partial derivative fx and fy, they are 0. Okay, so what am I going to do now? So we know that these two are belongs to D, and D is an open connected set. So we know that x1 y1 x2 y2 can be joined by uh, line segments which are either horizontal or vertical. Okay, fine. So this is what I have. Fine. So now let's try to draw a picture and then try to imagine the situation. So let's say I have this one, and let's say there are some holes here. Okay, just to make the picture a little bit complicated. So let's say I have this, and let's say I have the point x over here and I have the point y over here. So what am I proposing? Sorry, not x1 y1 x2 y2. So let me write the point as a comma b, maybe. So this, let's say this is a and this is b. Okay, so what I have, I will be able to go from a to b by means of horizontal and vertical line segments. Okay, so this is what I have. Okay, great. So now let us try to observe what we are going to have. So I want to say that at the point A and at the point B, the functional value is going to be the same. Okay, so what am I going to do? So first of all, can you say that if the functional value is going to be the same at this point A and this particular point? So for example, can I say that the functional value is going to be same at the point A and the point which I have circled? Can you say that? What do you think? Can I do this? Yes?
By mean value theorem, we can.
Hello? So can I say that the value at the point A and the point which I have circled, the functional value is going to be the same? That's my question.
Yes, sir.
Yeah, so how do
By
I?
mean value theorem, we can do this.
Yeah, by mean value theorem. Exactly. So what is the coordinate of the circular point? So the circular point, so if A is equal to x1 comma y1, then this circular point that I have written, so that will be
x1 plus h comma y1.
very good, x1 plus h comma y1. And then if I now it's just a line segment, it's I can treat my function here only one component is changing, which is the x component. So if I treat this as a function, means on that set, if I treat my function, it's only real functions of real value, means functions taking value in R. So if I treat that function, like restrict that function onto that set, it's just going to be a function of one variable taking values in R. And therefore and I know that my here if I take the derivative, it's only going to what I'm going to get, it's only fx, and I know fx is equal to 0. So if I use mean value theorem, I'm going to get across all this line at all the points my functional values are going to be the same, right? Yeah, even that is not necessary. I really need that the functional value at a and the point at which I have circled, at these 2 points the functional values should be the same. Agreed? Do you all agree that at the point
Yes,
A
sir.
and at the point O, whatever I have written, there the functional values are the same, right? Okay, great. Now, if you
Yes.
agree to that, will you also agree that if I say that the functional value at A and functional value at the point delta, that is also same?
Yes.
Yeah. So if you can't see, delta is this one. Yeah. You will agree to that?
Yes, sir.
Yes.
Similarly, now, can you tell me what is the functional value at delta and let's say the functional value at this square?
Also same.
Same. So if I keep doing this, what am I going to get eventually?
Function value of A is equals to function of value of B.
Very good. So you see what is the power of this the polygonally connected thing, correct?
Yes, sir.
Yeah. So therefore, what we have seen is that essentially, so this is a proof which I'm not elaborating too much, but you know what is to be done essentially. You have already seen this in means real analysis. So the same thing tells me that if I have a function which is one variable, means real functions of two variable but taking values in R, and then if the partial derivatives vanish identically, then what I'll get is that the function is constant on D. Okay, so no matter what which 2 point you choose, I'll be able to connect them by means of horizontal and vertical line segments. And now if I apply our mean value theorem of one variable, then we will be able to say that okay, just because the means when you apply mean value theorem, you get that the difference of the functional value at 2 points divided by the difference of the coordinate is equal to derivative at some point which is in between, but the derivative vanishes identically. So therefore at these 2 points the functional values are the same, and you can keep doing this and eventually you are going to get that the functional value at any 2 point of my set is going to be same. Fine. Okay, so of course in the proof we understand that D is something means that we are using this property that it is an open and connected set. Okay, so for example, now in this lemma, can I drop, let's say, let us take D to be open, but can I drop D to be connected? Of course, the proof might not work, but do you think we will be able to drop D being connected? Can we drop this hypothesis?
No, sir.
Why? Why can't I do that?
We take, sir, a union of two connected sets.
And
So, sir, function may not be constant.
yeah, so the idea is that see, whenever you have this kind of scenario, no, you can imagine one typical kind of example. So let's say I have the set which is open set and union of two disjoint open connected components. Then in this component I can give my functional value to be 1. In this component I can give my functional value to be 2. And you see that these are real valued function, partial derivatives are vanishing, but the function is not constant, right? So therefore like you of course very naturally see why being connected is also rather an important feature, and that's why I said for most of the cases we are going to work with open and connected subsets. Okay, so is this clear what I said? Fine.
Yes, sir.
Yes.
Okay, great. So we have this, and now let me write down one obvious statement probably. So that one is the first proposition, that let D be a domain and f belongs to H of D. So that's a holomorphic function. If f prime of d is identically 0, then what can I say? So f prime is identically 0 on d, then what can I say? Tell me from real analysis what you would have guessed. Constant. Okay, so here actually I really don't have to give a separate proof. So because here what I know, so if you want a proof, the proof would be very simple, because I know that f prime at z naught, we have just seen that f prime of z naught is nothing but fx at z naught, and if prime at z naught is identically 0, so that means fx of z naught is identically 0. Now fx of z naught I can write it as ux of z naught plus I times vx of z naught, where f is equal to u plus iv, and fx is now fx at z naught is 0 for all z naught in D, implies ux at z naught is equal to 0 is equal to vx at z naught for all z naught in D. And now this is about the partial derivative of u and v with respect to x. Now what can I say about the partial derivative of u and v with respect to y?
0 by using
Why?
CR equation.
Also 0.
Why?
Because of CR equation.
CR equations.
Very good. So it is given that f is holomorphic, so it satisfies CR equation, so that implies uy of z naught is equal to 0 is equal to ux of z naught for all z naught in D, as f satisfies CR equation. Okay, so very nice. So I get now this u and v, these are real parts of real and imaginary parts of a holomorphic function, and we see that they vanish identically on the whole of D. So what can I say about u and v separately?
Constant.
Each of them are constant.
Lemma 1
Are constant on D. So this follows from, where do I get this from?
above lemma.
Yeah. So this is what I get from lemma, and u and v are constant, that implies f is constant. Great. So we have this one, very nice. Okay, so now let us see a few more similar kind of observations. Okay, so that's, sorry, where did I go? So that's proposition 2. Okay, so what do I want to say here? So now here I have seen that if I have essentially, if I have two of them, both real part and imaginary part being constant, we see, of course, that will imply that f is constant. Okay, but in fact we have something even stronger. Okay, so the next proposition is going to be stronger than this. What is the next proposition? Next proposition says that, let's say again, D is a domain and f is holomorphic on D. So then what it says, if f is equal to u plus iv and u is constant, then f is constant. Okay, so what it turns out that to make f to be constant, it's good enough that your real part is constant. Okay, and I can write similarly, if v is constant, then also f is constant. Okay, so if one of the real part or the imaginary part is constant, then I can say that our function itself is going to be constant. Okay, so now quickly complete this proof. Yeah, complete this proof quickly.
By CR
Yes,
equation.
when ux equals to 0 और uy equals to 0, then आप वहाँ से conclude कर देंगे bx and vy is equals to 0, then f and b u and v constant, then f is constant.
Okay, so how did we get this next line? Second line, how did we get?
CR
By CR.
Good. So that implies again now I have both these things. So this implies V is constant, and therefore it is constant. Okay, great. So and what about the other way around? If I start with V being constant, again the same proof, right? Same proof. Okay, so either you can do that, or you can also say in a different manner that, for example, if U is the real part of F, where F is a holomorphic function, then V is the real part of minus I times F, right?
Yes, sir.
So you can then apply the same statement. So often like this kind of possibility of changing the role of U and V, that plays a role. So this is something which you can remember. Okay, so that's good. Now we have this proposition which we get. So it says that if one of them is constant, then also we are going to get that the function itself is constant. Okay, so now let's have the next proposition, proposition 3. So what is that? Let D be a domain. Okay. D domain, and F is a holomorphic function. Now this time what I am assuming is that such that mod of F is constant. Okay, so D is domain, mod of F is constant, and then also we will be able to say then also we have F is constant. Okay, so if the modulus absolute value is constant, still we will get that our function is constant. Okay, so that means if you know, for instance, that your function, let's say I have a domain and your function takes value on some circle on circle of some radius centered at 0. Okay, so let somebody tells you that I have a function defined on some open-end connected set D, which takes values in like on a circle of radius something centered at 0. Okay, then immediately you will be able to say that okay, my function has to be constant. Yeah, so is it clear what I am saying? Yeah, so for example, means in the kind of application which I was trying to give you, that if I have a function which is starting from a domain and taking values on a circle, okay, of some radius centered at 0, that means no matter what is your function, when you take absolute value of F, that has to be constant, right? So if you take a circle of radius r centered at 0, on that circle, what is common? The common thing is that absolute value is same for all point. So therefore you get that the absolute value is constant, and once the absolute value is constant, by using this proposition 3, you will get that your function itself is constant. Fine, great. So now we have this, and let us try to prove this one. Okay, so proof. So if, for example, so what is mod of F? Actually, we are not going to work with mod of F. We are going to essentially work with mod of F square. Okay. So for example, if mod of F is equal to 0, that implies what? So if mod of F is equal to 0, so mod of F square is equal to 0. So that means what is mod of F square? If I write F as U plus IV,
Plus V square.
U square plus V square.
very good. So mod of F square is U square plus V square, which is equal to 0 on D. So this square is equal to 0 on D, and that implies what? U and V are real valued function. So therefore, what?
We are 0.
Both are 0. So this implies U and V are identically 0, which implies F is identically 0. Fine. So if mod of F is constant, and if that constant is equal to 0, sorry. Hello, somebody saying something? Okay, so if U and V are identically 0, so F is identically 0. So in this case, we are done. Okay, so we can assume that mod of F is not equal to 0. Okay, so let mod of f square or mod of f is not equal to 0. So u square plus v square is not equal to 0. So this is some number which is non-zero. Okay, but this is constant, of course. Okay, it's given to be constant. Okay, fine. If this is constant, what do I get? Tell me quickly. So for example, if I differentiate this one, if I take the partial derivative with respect to x, what am I going to get? I'm going to get 2u ux plus 2v vx is equal to 0. So which I write it as u ux plus v vx is equal to 0. And similarly, I get that uy plus v vy is equal to 0. Okay, I have these two things. Okay, so I get these two equations. And now what am I going to do? I am going to do the following. So I will see that we have CR equation. So what does CR equation gives us?
ux equals to vy and uy equals to minus vx.
Y equal to minus Vx. Very good. So if I replace, let's say, in this, then what am I going to get? U into ux minus v into uy is equal. So let's call it 1. And then I also get u into uy minus plus v into ux is equal to 0. So let's call it number 2. Okay, fine. Now what am I going to do is the following. So you have this kind of equation, you know how to solve. So for example, 1 into v minus 2 into u, if I do, what am I going to get? So this implies, tell me, if I multiply by v to this and u to the next one, then this term is going to get cancelled, and therefore I am going to get minus of uy, right? I'm getting this. Very good. And I have assumed that u square plus v square is not equal to 0. So this implies uy is equal to 0. Agreed, all of you?
Yes.
Similar.
Yes,
Let us remove these two lines. Yeah. Okay. Now if I do the similar thing, let's say I multiply 1 times u plus 2 times v, then this implies what? And this implies if I multiply by u, and then so therefore these two terms are going to get cancelled, and therefore what am I going to get is that ux times u square plus v square is equal to 0. That implies ux is equal to 0. And once I have that, what can I say now? Once I have ux equal to 0,
F is constant.
Vi equal to 0.
Also,
Vx equal to 0.
yeah, so I can say ux, so that implies u is 0, or sorry, u is constant, and therefore if is constant, I can use the previous proposition, or I can just say ux uy is 0, so vx vy is 0, so uv are constant, so if is constant anyway. Okay, so therefore we see that if, for example, somebody tells you that we have a holomorphic function defined on a domain taking values on a circle, then circle centered at 0, then you will immediately say that f will be constant. Okay, and remember here also again that, for example, if you take your set, like your starting point, to be something which is not connected, you will still not be able to say the same thing. Okay? Because, for example, what you will see is that if I start, if I have my means starting set, so that to be union of two disjoint connected sets, open connected sets, then in one set you can define something to be 1, in the other set you can define something to be -1, but as a whole mod of f is constant, but f is not constant, right? So therefore that our set D is connected, that is really important. Okay, fine. So let us see now what we are going to do. We are going to so we have seen some examples of these phenomena, this or the applications of CR equation. So I will upload probably today some tutorial sheet. So there you will have similar kind of problems. You should do them. And the next thing that we want to pursue is called, like, we will now see some non-trivial example of holomorphic functions. Okay, so in fact, as we will prove later, these are going to be the only examples of holomorphic functions. Okay, so some, as I said, some non-trivial examples. So moving on from CR equation, some non-trivial examples of holomorphic functions. Okay, so we move to this, and like I had promised, so this is going to be about power series. Okay, so let's begin with the formal definition. So what's the formal definition of a power series? So a formal power series, so when I say a formal power series, that means we are not going to bother about convergence at all. So it's just a symbol. Okay, so a formal power series is a series of the form summation n bigger than or equal to 0, a n z power n, where a n's are complex number, and z is an indeterminate. Okay. So formal power series means just some infinite sum without any meaning. Okay, so here z is just an indeterminate, it is not any complex number, it's just an indeterminate, and I have an infinite sum like this. So it's essentially, it is a symbol. Okay, so if I like some, means if you write polynomials, so in general you can treat polynomials. So similarly, at this moment I am not treating this as a function at all. Okay, so it is only a formal sum. Okay, now if I want to use them, I have to make sense of their convergence. Okay, so it's of course clearly written in terms of an infinite series. Now if I want to use them, I must try to find out a meaning of this guy. Okay, so let us try to do that, and let's try to do this by means of some example. Okay, so for example, so to give a meaning to this formal power series, so what we are going to do, so let's see, that's our next objective, to give meaning to this one. So let us begin with an example. Okay, so let us consider n bigger than or equal to 0, z power n. Okay, so let's begin with one of the simpler one. Okay, fine. We would like to understand if I take this formal power series where the coefficients, each of them are equal to 1, can I say something about them? Okay, and now exactly like when you were dealing with infinite series in your real analysis course, the definition of convergence of infinite series came from considering the partial sum of the infinite series, correct?
Yes, sir.
So here also we are going to do the same thing. Okay, so we are going to begin by considering partial sum of this guy. Okay, and we will see if we can make sense of the partial sums at all. Okay, so at this moment still I am not, as I said, I am still not taking my z to be any particular complex number. It's still an indeterminate, and I'm going to take only partial, like the finite in the first few terms of this infinite series that I have written, and I will try to see if I can make sense of that. Fine, let's try doing that. Okay, note the partial sum 1 plus z. So z power 0 means 1. Okay, so that's our understanding. So let's say if I go up to z power n. Okay, so can I say something about this? So I see that if I take this one and if I multiply this with 1 minus z, I'm going to get, tell me what, 1 minus z power n plus 1, correct?
Yes, sir.
Okay, so now once I have this, let us try to understand what is going on. So now if I take some specific values of my indeterminate z, so now if for example mod of z is less than or equal, let's say strictly less than 1, then what can I say? What can I say about the right hand side? Yeah,
One.
it's going into 1, right? So I can say that 1 plus z square, so on and so forth up to z power n times 1 minus z goes to 1 as n tends to infinity. Correct?
Yes,
Okay.
sir.
Yes, sir.
In other words, so if I say, so this guy 1 plus z so on and so forth up to z power n, this goes to 1 upon 1 minus z. Okay, as n tends to infinity. And remember here I have taken mod of z less than 1, so 1 minus z is something which is a non-zero quantity, so I can divide by this, no problem. Fine. So what it turns out is that, so we see that the power series is very basic. Summation z power n bigger than or equal to 0 converges for mod z less than 1. Okay, and exactly if you take mod z which is bigger than or equal to 1, then this is not going to converge. That also we will see. So we all of us agree that this power series converges for mod z less than 1, right? This geometric series you have seen so many times in your life. Okay, fine.
Yes.
Yeah. Now if mod of z is let's say bigger than or equal to 1, then what can I say? Then for example mod of z n, this one does not go to 0, right, in particular, yeah, this one does not go to 0 as n tends to infinity, and hence what I will get is that this series mod of z power n bigger than or equal to 0 does not converge. Or yeah, even I can say this is true for, I don't have to bother about this, I can say that z power n does not go to 0. So I can even say that this does not converge. Does not converge for mod z bigger than or equal to 1. Fine. All of you will agree to this? Yeah. See,
Yes, sir.
Yes, sir.
we are having two phenomena. Okay, so if I try to draw a picture, so this power series seem to be having a phenomena that, let's say this is, let's try to imagine this is the ball of radius 1. Okay, so I see that as long as I'm taking points inside this ball, my function is this formal power series is making sense, it's converging. And the moment I am taking outside the ball, okay, so I'm not at this moment talking about the boundary, but the moment I'm taking outside this ball, the function, the formal power series is diverging. Okay, or it's not converging, let's not use the term divergent. So in the formal power series does not converge. Okay, so it seems that there is a threshold, right? So this 1 is the threshold that as long as you are smaller than 1 in absolute value, your infinite series is convergent, and the moment you go beyond 1, your infinite series is going to that infinite series is not going to converge. Okay, so this is this threshold is called the radius of convergence. Okay, so here in case of this series, the radius of convergence is for example 1, you can see that, and this particular threshold is going to be called radius of convergence. Okay, so now how do I find what is this radius of convergence? So what I am going to say is the following. Okay, so more precisely, okay, so how am I going to find this radius of convergence and all that? Okay, so consider the set Okay, so this is a set of set of non-negative real numbers. Okay, set r bigger than or equal to 0 such that mod of n bigger than or equal to 0, mod of an r power n is finite. So consider this set. Okay, so I'm considering a set r bigger than or equal to 0 such that mod of like where summation n bigger than or equal to 0 mod of n r power n is finite. Right? So I'm taking this set. Yeah. Now, what I'm trying to say is that first of all, this set that I have denoted over here, this set is going to be non-empty. Why? First of all, why this set is non-empty?
0 is there.
Very good. So this set is 0, non-empty. Okay, so this is non-empty. Fine, non-empty. Good. Okay. Now, can you also say, for example, that my next claim is that this set is an interval. So this is a subset of r bigger than or equal to 0. Now my claim is that this set is an interval. Can you show that this set is going to be an interval?
Only singleton होगा तो फिर कैसा इंटरवल बनेगा?
Okay, so in that case I allow, like, my interval can be closed interval AB where A is equal to B. So that I allow. Okay, so but if you don't have like, you take that, and then can you say why this set should be an interval?
If you take any point in the set, for that point power series is convergent. So from that we can say that this set is connected. Interval. Sorry.
So first of all, tell me what is the definition of an interval? Huh?
For any 2 point from the set,
Good.
with any point within that 2 points belongs to the original set.
Absolutely. So what is an interval? An interval is a set, so subset of R, such that if you take any 2 points from that set, all the points in between those two are in that set. So if I can say this, then like, that's the defining or that's the definition of an interval. So it's a subset of R such that between any 2 points of that set, all the points which lie between those 2 points in R, all those points should be in that set. Okay, so if you take this definition, then singleton 0 like is an interval. Okay, without any problem. So this one is an interval. Why this is? Now if you take this definition, why this is an interval? Now can you tell me? For example, it's, let's say I take some R which is in this set, which is positive. Then how can I say that all points between 0 and R, all those points are going to be in this set?
By comparison test.
Very good. This is what I wanted to hear. Okay, so this is an interval by comparison test. Very nice. Okay, so therefore this one looks like this is an interval. Now this could be bounded, this could be unbounded, I do not know. So if this set is unbounded, we set the radius of convergence of the power series is infinite. Okay, so that is what is my definition now. And in this case, tell me if you agree to this or not. The power series an z power n bigger than or equal to 0 converges for all z in C. Can I say this? If this set is unbounded, then I call that the radius of convergence of the power series an z power n is infinite. And my claim is that in this case, summation n bigger than or equal to 0 an z power n converges for all z in C. How can I prove this? Yeah. The proof is very simple. Okay, so for example, what am I going to do? I'm going to start with some Z0 and I am going to show that at Z0 the power series not only converges, it converges absolutely. Okay, so let Z0 belongs to C. Consider R bigger such that R positive such that mod of Z0 is less than R. Okay, since supremum of that set, whatever that set I had, so let me call it R0. Since this set mod of an r power n bigger than or equal to 0, since this supremum is infinity, what can I say? Tell me, what can I say about R0? Hello, are we connected?
Yes, sir.
So
Yes.
infinite, what can I say? Sorry, this is finite. I should write this is finite, which is infinite. Okay, so then what can I say? I can say that summation n bigger than or equal to 0 mod of an R0 power n is finite. Correct? Do you all agree to this? Yes or no?
No.
Don't tell me why.
Sir, please repeat.
How is it?
Yeah, so what have I started with? I said that this supremum is infinity, right? So if some set
Yes.
some supremum which is equal to infinity and you start with any point R0, that means that set has a point which is bigger than R0. Correct? Yes.
Yes.
So choose R1 from this set which is bigger than R0. So that means what? Okay, so let me write one more step. So there exists R1 in this set. Okay, the set I am not writing again, such that R0 is strictly less than R1. Agreed? Fine.
Yes.
So that implies what? At R1 I can say n bigger than or equal to 0 mod of an R1 power n is finite. Correct?
Yeah.
Now somebody said already use the term which I wanted to hear was comparison test.
Comparison.
Yeah. By comparison test, n bigger than or equal to 0 mod of an R0 power n is finite. And once I have this, can I say again use comparison test and get what? Mod of n bigger than or equal to 0 mod of an mod of Z0 to the power n is finite.
Mm.
Okay.
Yes.
And once this is true, that implies we know what absolute convergence implies.
Convergence.
Condition is.
So this one is also convergent, correct? So therefore, no matter what point in the set of complex numbers I start with, I will get that the infinite the power series converges. Agreed?
Yes, sir.
Yes.
So therefore, please go through this. This is just repeated use of comparison test. There is absolutely nothing here. So if you start with a power series for which this particular set, okay, that I have written over here, which is an interval I said already, this set, the moment this set is unbounded, okay, so in fact it is closed interval 0 to infinity actually. So if it, since it is interval and it's unbounded, you are going to get that this set is going to be in that case closed 0 open infinity. So anyway, in that case, we set that the radius of convergence is infinite. And in this case, what I see that the power series converges for all z in the complex plane. Yeah, that's number one. Now, if we set, or next if we have, okay, I'll stop here for today. Next, if we have this set is bounded, okay, the set I am not writing, so let me give it a name. Let us call it S. It's very clumsy that I'm writing each time this interval. Okay, so let's call it S. So now if we have S is finite or S is bounded, then so it's a subset of set of real numbers and it is bounded. So that means what? What can I say about a set which is bounded? Yeah. Very good. So then supremum S exists in R. Okay, let R or capital R equal to supremum of S. Okay, then R is called the radius of convergence of summation a n z power n bigger than or equal to 0. Okay, now that's the definition. Okay, that when we take set of I have a formal power series, you look at the set S and take its supremum. If it is unbounded, anyway supremum is going to plus infinity, that's by definition. So you take the supremum, and the supremum, whatever it is, whether it is a real number or plus infinity, you are going to call that to be the radius of convergence. Okay, and now when the supremum was infinity, we saw that the power series was convergent on whole of C. And in this case, this is an exercise which I will leave it to you to do. Okay, and stop that, show that for all z in C such that mod z is less than R, we have summation n bigger than or equal to 0 a n z power n is convergent. In fact, absolutely convergent.
Yes, sir.
Okay, so here something I'm saying something very precise, means, or like you have to pay a little bit attention. Here I am saying mod z is less than R. I'm not saying less than or equal to. Okay, so anything which is below R, there in absolute value, I will be able to say that my series is absolutely convergent. And if mod z is bigger than R, we have summation n bigger than or equal to 0 a n z power n does not converge. Okay, so this R is a threshold for a power series. This radius of convergence is a threshold. The moment you go slightly below R, you will have absolute convergence, and the moment you go slightly above R, you can have various possibilities. Okay, so it may so happen that, for example, your set S to start with could be a closed interval, and therefore the supremum is going to be right endpoint. But it may so happen also that your set S for some particular power series could be open on the right side. Okay, now once your set S is open on the right side, then what will happen is that then on the boundary, like for those points mod of z equal to R, there could be several possibilities. It may so happen that on the boundary your at some point the power series might converge, at some other point the power series might not converge, and several other things. So those things I will explain by examples, okay, in the next class. So for example, here I can just say I was taking this z power n in this power series, the set S. Can you tell me what is the set S here? Close 0, then sorry,
Open one.
Open one.
Open one.
so this is the set in this particular case. So you might get, there will be cases where you will get closed as well. For example, if I take Zn by n squared, then your S will be closed. So I will give all these examples in the next class, don't worry. But at this moment, try complete proving this. Okay, I have already told you the essential results that you need is going to be comparison test, but you have to carefully write things down. Okay, remember, at the point which is the supremum of this set, I have no information about convergence. Okay, I only have the knowledge that no matter which point you take in S, the series converges, but at the supremum I have no information. Remember this very clearly. Okay, so and keeping all this in mind, try to complete this exercise, and we will meet next on Monday. I will upload a tutorial today, and try to do some of the exercises from there, and also discuss with your tutor. Okay.
Hello, sir.
Yes.
Sir, in this example, sir, domain of convergence should be open -1 to close one, open one.